Imagine solving a complex puzzle not by talking about it, but by visually drawing out the steps. This is the core concept of native visual reasoning, where visual states like images and videos serve as the primary medium for problem solving. To make this paradigm trainable and controllable, researchers have introduced VBVR-Pro. This closed-loop testbed provides a unified environment to scale, evaluate, and optimize visual reasoning models. By treating visual generation as a first-class substrate for reasoning, it moves us beyond purely language-centric AI models. A major bottleneck in current visual reasoning research is that existing benchmarks are primarily designed for evaluation rather than training. They offer very little training data, and what does exist often focuses on simplified symbolic settings that do not transfer well to real-world tasks. Furthermore, we lack reliable ways to evaluate generated visual outputs, making it difficult to provide constructive feedback to models during training. VBVR-Pro addresses these gaps by offering a massive, scalable source of training data paired with precise, automated feedback. To solve the data scarcity problem, VBVR-Pro features a controlled task space of 300 procedurally generated tasks. These tasks are organized around 5 core cognitive faculties: perception, spatiality, transformation, abstraction, and knowledge. Each task is implemented as a programmatic generator with randomized parameters, ensuring high visual diversity. Because the underlying parameters are known, the system can automatically compute the correct solution trajectory, providing rich, programmatically derived supervision without the need for manual human annotation. Evaluating visual reasoning is notoriously difficult, and relying on vision-language models as judges often leads to critical failures. The researchers identified 3 common failure modes of the VLM-as-a-Judge paradigm: imprecise visual perception, oversight of fine-grained details, and complete misunderstanding of task rules. Additionally, VLM judges are highly expensive to run at scale and lack reproducibility, often giving different scores to the exact same video. This makes them highly unsuitable for guiding reinforcement learning algorithms. To establish a trustworthy evaluation metric, VBVR-Pro introduces deterministic, rule-based verifiable reward scorers. Instead of analyzing raw pixels directly, these scorers use classical computer vision techniques to extract semantic entities, such as object colors, shapes, positions, and counts. The scorer then applies task-specific rules to evaluate both the final state and the intermediate process. This semantic design makes the scores highly interpretable, completely reproducible, and exceptionally cheap to compute compared to large model API calls. A key feature of VBVR-Pro is its ability to render the same underlying task into different visual modalities, allowing for a fair comparison between image, video, and interleaved generators. The image modality is structured into 3 distinct regimes: last frame for simple outcomes, keyframe for step-by-step transitions, and multi-frame for continuous processes. The study reveals that while video generation excels at tracking complex spatiotemporal states, interleaved text-image generation offers a highly compute-efficient alternative by externalizing intermediate visual states. Because the verifiable scorers are fast and deterministic, they can be directly integrated into reinforcement learning pipelines as reward functions. The researchers developed a framework called Reinforcement Learning with Verifiable Rewards, or RLVAR. To enable effective exploration in visual space, they utilized coefficients-preserving sampling, which introduces semantic variation without destroying visual quality. The results show that RLVAR leads to steady, stable performance improvements, whereas training with VLM-based rewards quickly stagnates due to unpenalized visual artifacts. A crucial finding of this research is that models trained on VBVR-Pro exhibit strong transferability to external, real-world benchmarks. Models achieved consistent performance gains of up to 20 percentage points on held-out datasets like Rise Video and Baby Vision. To ensure the models were not simply memorizing patterns, the authors conducted a nearest neighbor analysis. This confirmed that the models learned abstract, reusable visual concepts and operations rather than superficial instruction templates, proving the value of a diverse procedural curriculum. In conclusion, VBVR-Pro establishes a powerful, closed-loop foundation for scaling native visual reasoning. By providing a massive suite of 300 procedural tasks, reliable rule-based scorers, and a robust reinforcement learning framework, it opens up new pathways for training generative AI. While current models still perform below human levels, this suite provides the necessary infrastructure to drive future breakthroughs in spatial planning, physical understanding, and embodied AI systems.